All right, guys, so what we're looking at today is, again, dealing with more radicals. But before we get into that, are there any homework questions? Yes. 5.1, part 2. Question number 36. Get the calligraphy pen out. 5x cubed is equal to 1080. So we're solving this one here. And round your answer to 2 decimal places when appropriate. So we're just looking for the real solutions. So the first thing we can do here is divide both sides by 5. Because we're wanting to try to get x by itself. So that'll tell us that x cubed is equal to 2 would be 10, 1, 6. So we get 216. Now at this point here, to get rid of the 3, we need to take the cubed root of both sides. And x to the cubed root of x cubed will be x is equal to, I think it's 6. 6. Now, this here is the answer. We would just need to make sure and look at the root we take. Because it's an odd root, it doesn't need to be plus or minus. Because whenever we have an odd root, if what's inside is negative, we only have one real root. If what's inside is 0, we only have one real root. And if what's inside is positive, one real root. Because odd, it's only going to end up being one real root. The only time we add the plus or minus is if we have an even root and what's inside is positive. If we have an even root and what's inside is negative, we technically have a solution, but because the directions here are asking for real roots, we have no real roots. It doesn't work out. Does that make sense? Yes. Any other questions? Or any other ones that y'all want to look at? Okay. Now, we talked about this already, simplest form, because it's not included in the notes there, but I'm, again, reiterating this here. Because, again, what we're talking about today and working with today is making sure that they're in simplest form. And this is something that does come up on the ACT, they'll give you radicals, rewrite in simplest form. So, no radicands have perfect nth powers as factors other than 1. If we can take the root, we need to take it. So for square roots, we can't have 4 inside the square root, or any number that has a factor of 4. If we can reduce it, we need to reduce it. No radicals or no radicands can contain fractions. So again, I can't have the square root of 3/4. And no radicals appear in the denominator. Well, these here, 2 and 3, really go together. Because, and we'll see that here in a minute. So really, the first one is the radical can't simplify down. We need it to where it can't. So I can't have the square root of 4 left over. I can't have the cubed root of 8. If it can reduce, we need to reduce it. And we can't have it in the bottom of a fraction. Now our product property states that the nth root of a times b can be rewritten as the nth root of a times the nth root of b, which y'all done before. Y'all did that in Algebra 1, where we can break radicals apart and put them together. But the key is that the index of the root has to be the same. When we multiply or divide, that for us to be able to put them together or pull them apart, that root has to stay the same. And the same for quotient. When we divide, either going this way, splitting them up, or going the other way around, the root has to be the same. And this is why, when I said a minute ago that the second and third one are essentially the same thing. Because we can't have a fraction inside of these radicals. Well, realistically, if there's a fraction inside of the radical, It's the same as saying that we're having a radical in the denominator. We can't have a radical in the denominator, because it's essentially saying we have a fraction. And there's different ways that we can go about doing this in the properties that we dealt with yesterday. Some of it, if the number, like we see here, well, 162 is divisible by 2. Instead of trying to take the fourth root of 2 or trying to see if we can simplify that, well, I can actually merge them back together and divide. Because 162 divided by 2 is 81. Okay, now I can deal with that. I've gotten rid of all of the radicals in the denominator because I don't have a denominator other than 1. Does that kind of make sense? And again, a lot of this here is not a set, this is how we do it every single time. It's looking at the numbers and what do I need to do to manipulate it so that it is in simplest form. And again, the more that you look at the numbers, the more we'll be able to figure this out and rationalize your way through it. Because looking at the first one here, and again, because I've talked to Ms. Kendall about this morning, because there are different ways we can do this. Now, our product property says that we can take the 12 and 18 and multiply them together and then simplify it that way. That's one way we can do that. Another way is looking at these as their prime factorizations. The smallest number we can write them together. And I like that way a lot because multiplying 12 and 18 together, most likely we're going to end up having to use a calculator and then simplifying back down. And I feel, for the most part, that y'all are good with multiplying like bases and adding the exponents. So if we look at 12, the smallest number that goes into 12 is 2, and it would be 6. And 6 is 2 and 3. So really, I can say that the cubed root of 12, well, we have 2 how many times? Twice, so that would be 2 squared times 3. Because 2 squared times 3 does give us 12, yes? Now the reason we're doing that is because, again, whenever that exponent and the root match up, we can simplify that, yes? So if we had 2 to the third, the cubed root of 2 to the third would be 2. And if we had the cubed root of 3 to the third, that would just be 3. Okay. Times. We can do the same thing with 18. I'm going to erase the 12 so I have more room. 18 is 2 times 9, and 9 is 3 times 3. So we do have 1, 2, and it's being multiplied by 3 squared. Any questions on any of this here? Because we feel comfortable with factor trees and breaking them down to our prime factorization, yes? Now our product property states that we can multiply these together. Well, if I multiply 2 squared by 2, I'm going to have what? 2 to the third. Because when we multiply like bases, we add the exponents. And 3 times 3 squared would be 3 cubed. Any questions on this here? Well, what is the cubed root of 2 cubed? 2 times cubed root of 3 cubed would be 3. Well, 2 times 3 is 6. So this one here, we could have actually done this in a calculator because we came out to a whole number. But that's it there, because I mean, really, get a highlighter. At this point here, we could have multiplied them together, split them back apart to where we have the cubed root of 2 cubed times the cubed root of 3 cubed. Okay, we get 2 times 3, which is 6. Questions on this here? And I think most of this you've done. You've done most of these here in Algebra 1. We've done these before. We didn't get into fourth roots, fifth roots, sixth roots, but it's not any different than square roots and cubed roots. We're just looking for exponents of higher than 2 and 3. Any other questions on this here? Well, we know the first one's simplified because, well, we don't have any radicals anymore, so we don't have to worry about any of the simplifying properties. Now the next one, okay, it's definitely not simplified because we have a radical in the denominator. Can we take the fourth root of 5? Can we take any root of 5? No, it's prime. Will 80 divide by 5 evenly? Yeah. So here it's like, okay, so those will simplify nicely. Because if they will, let's go on and combine them. And what I mean by that is saying that we have the fourth root of 80 divided by 5. Now, if they won't simplify nicely, because if it had been, say, 7, there's not a whole lot of use in doing this because it doesn't help us. It does not make it into a simpler problem. But here, since 80 does divide by 5 evenly, 80 divided by 5 is 16. That was 15 seemed weird, but 16, yes? Okay, because doing that division did make it easier to work with. We'll see some later where that's not the case, and we'll do that a little differently. Well, now we just need to take the fourth root of 16, and we're done. And again, we can plug these into the calculator to see if they do get us a whole number or break them down to that point. If they don't, if we'd gotten here and the fourth root of 16 didn't come out to be even, then we can do factor trees to break it down there. Questions on this here? So we have the cubed root of 4 and the cubed root of 128. So if we wanted to at this point, we could type that into the calculator and see what we get. And individually, we're not going to be able to take the cubed root of 4. It's not going to come out to a whole number. And the cubed root of 128 won't either. They're close, but they won't get there. Because we can type it in and get 8, because it does come out to be a whole number. And let's see why. Now, we know that 4 is 2 squared, because we can take the square root of 4 and get 2. Now, 128, we know is divisible by 2, yes? Because it would be 2 and 64. Is 64 a perfect cube? Okay, so, well, we can keep going, say 2 and 32. 32 is 2 and 16. 16 is 2 and 8. 8 is 2 and 4 is 2 and 2. Well, we get what? 1, 2, 3, 4, 5, 6, 7. Third root of 2 to the 7th. Okay. Now, when we multiply like bases, we add the exponents. So 2 plus 7 would give us 9. We get 2 to the 9th, yes? Now, if we took the cubed root of it, what would we get? Because that's a little hard to see, yes? If it's a little hard to see how this reduces, well, we do have our rational exponents, yes? What would the numerator of this rational exponent be? Number on top would be the 9, and the denominator would be our 3. And this is coming from our, I'll end up erasing this, the nth root of a to the x is equal to a to the x over n. The denominator of our rational exponent is whatever the root is. Nth root of a to the x is equal to a to the x over n. So if there's an exponent inside with whatever we're using, it goes on top and the root goes on bottom. So looking at this here might be a little bit easier to see it because 9 divided by 3 is 3, and well 2 to the third is 8. And sometimes thinking about them as rational exponents can make it easier to see how will they simplify. And even if it's not a whole number, like 3 here, so I'm going to get a new page, because if we had, say, 2 to the 10 thirds, well, that's one more, yes? Well, 10 thirds as a mixed number would be 3 and 1/3, yes? So we know 3 of those 2 should come out of the radical. So really we can say that this is 2 to the third times 2 to the 1/3, because it's telling us how many are left over. Well, as we just saw, 2 to the third is 8, and 2 to the 1/3 would be rewritten as the cubed root of 2, because if we have any left over, they're going to go back into the radical, because they don't come out. And we can kind of see it that way. Or if we looked at this here and said, well, every group of 3 is going to come out, well, how many groups of 3 can we pull out of 9? 3. So we'd end up with 2 to the third, which gives us 8. So there are different ways to think about this. Any questions on this here? (192), the fifth root of 192 divided by the fifth root of 6. Does 192 divide by 6 evenly? Okay. And again, for this to be simplified, we can't have a radical in the denominator, and we can't technically have a fraction in a radical, or inside the radicand. But since they do divide evenly, putting them back together does help. Because 192 divided by 6 is 32. Okay, so that makes it simpler because now we don't have any fractions or radicals in the denominator. We've taken care of that. The only thing we need to determine is, can I take the fifth root of 32? Yes, and it is 2. So that would be our answer. Now, problems like this pop up on the ACT. It's kind of easy to determine if we're going to be able to plug it in. Because again, the ACT gives you 5 answer choices, yes? And if you look at all 5 answer choices and none of them have a radical, okay, most likely it's going to simplify nice and even, plug it in and you're done. If most of them do have a radical, especially if they have the same radical, it was like all of the answers have a radical of 3, well, we know that whatever our answer is going to be multiplied by the square root of 3, or whatever root of 3. So most likely, whatever the index is, so here the fifth root of 3, well, most likely I'm going to have a perfect fifth root times 3. Divide the number by 3, find the fifth root of that, and you're done. Does that make sense? So that's why, kind of like those tests, you can use the answer key to figure out the answers, figure out what the actual answer is. but a lot of times it's just breaking it down and simplifying. The yellow calculators can do this, but you have to write it in that form. They don't like having the radical with the fraction inside. If you split it apart and it is a whole number, most likely it'll work out. For some, it'll simplify. Any questions on this here? Okay. Well, let's look at the next one here. Cubed root of 135. If we type this in, we get a decimal. So these here, because these here, they want it in simplest radical form. And what that tells us is that we don't have a whole number cubed that'll give us 135. So let's see what we have. Factor tree, 135. What's a number we know for sure goes into 135? 5. It would be 5 times 27. Now, anytime you're doing a factor tree, if you spot a perfect here, it'd be perfect cube. We can really stop at that point. Now, 5 is prime. Is 27 a perfect cube? Most likely, but we can go on and see. Because what's one number that goes into 27? Because it'd be 3 times 9, and 9 is 3 times 3. Well, hey, I have 3 3s. So really what we're saying with the cubed root of 135 is that we have the cubed root of 3 cubed times 5 to the first. Now the textbook is not wrong in saying this, but they would use the property and say, okay, well this is the cubed root of 3 cubed times the cubed root of 5, because we're going to split it apart. And the cubed root of 3 cubed is 3. Can we take the cubed root of 5? Well, no. So it's going to be times the cubed root of 5, and that would be our answer. Because we're just trying to simplify those radicals. Not in simplest radical form. Simplest radical form wants us to reduce all the radicals as far as they'll go before turning it into a decimal. So we would still include radicals in. Because if we can't simplify the radical any further, it stays in the answer. Now the ones before where we got a whole number, that works because all the radicals simplified out. We didn't have anything left over. But here, because the cubed root of 5 doesn't simplify any further without turning it into a decimal, we leave it alone. Because that's the same as when we solved it last week where we left the 4th root of 21. It didn't ask us to approximate. It didn't ask to round. Simplest radical form is what it's asking for. Does that make sense? Okay. Let's look at the next one here. Obviously, we can't take the 5th root of 7. 7's prime, yes? Can I take the 5th root of 8? Well, no, because 8 is a perfect cube, because 2 cubed is 8, yes? Okay, because that's kind of nice to know. Will 7 divide by 8 evenly? Well, no, it's prime, right? But one of our simplifying rules says I cannot have a fraction inside of a radical, and I cannot have a radical in the denominator, yes? So we need a way to simplify this. Now, as we just said, 8 is the same as what? Erase that. Because 8, as we factor tree, would be 2 times 4, which is 2 times 2. We can say 8 is 2 cubed. Yes, so here, because 8 is 2 cubed, because really, realistically, if we can get that denominator to be a perfect here 5th root, then that radical would simplify out, yes? but 8 is 2 to the third, yes? How many more 2's do I need for it to really simplify out? Well, how many do we have right now? How many do I need to get? Because if I had 2 to the 5th, scroll down just a little bit, is in the denominator, if this was the 5th root of 2 to the 5th, then the 5th root in that 5 would simplify out because we'd have 5 over 5, yes? But how many do I have? So how many more 2's would I need? 2. So we can use our nice multiplication of 1 and multiply this by the 5th root of 2 squared. Well, I have to also do it on top. Is if I multiply those two denominators, 5th root and 5th root, so we can multiply, 2 to the 3rd times 2 squared would give us 2 to the 5th. Now the numerator would be the 5th root of 7 times 2 squared. Well, the 5th root of 2 to the 5th is 2, yes? Now the numerator, if there is any way that we could simplify it down, we will. But 2 squared isn't going to, we can't take the 5th root of it. And 7 we know is prime, yes? So we can't simplify anywhere there. So we would actually just go on and multiply those together. We could do that in a calculator, 7 times 2 squared. Well, 2 squared is what? 4. 7 times 4 is 28. I don't know why I just second guessed myself on that one. But, and that's it. Because if I know over here, highlighter, that we can't take the 5th root of 7 and we can't take the 5th root of 2 squared, and we know that 7 and 2 squared don't have any common factors, we can't take the 5th root of it. The only way that we'd be able to take the 5th root of the numerator is if for some reason the 7 had 2 cubed, had common factors in it, then we could have. But if the 7 had 2 cubed, we could have divided from the beginning and it would have worked out nicer. But that right there is it. Any questions on this here? Okay. Now, one of the things that y'all might think about is this here, we do have 8 to the 1st, yes? We could have used 8 to the 4th on top and bottom, but 8 to the 4th is really saying 2 to the 3rd to the 4th, which would be 2 to the 12th. Well, how many 2's did we actually need? 2. Every group of 5 2's would come out, yes? Which means top and bottom, I would be actually adding a 2 to the 10th, 2 to the 5th twice. Essentially, we're adding 4. We're going above what we would need, which would really just change this answer when we got down here to being 4 times the 5th root of 28 over 8. Well, 4 over 8 is 1/2. Do y'all see what happened there? Because just like last chapter where we talked about adding or solving by multiplying by more than what we need, or especially with any of those where we add terms, or they end up having to come back out later, that's what would happen if we ended up using 8 to the 3rd instead of 2 squared. We go above what we actually need. So we'll look at this one here. We'll go to the cubed root of 500 because I feel like these here, the fractions, are a little more challenging. And the really thing to think about with these here, 4th root, is rewriting them in prime factorization. Rewrite them as the multiplications up for that number as simplified or as small as we can get it and see what's missing. How much more do I need to add to it to get to the next root? Well, 4 is the same as 2 squared. 19's prime. So they're kind of nice in giving us like 19, these numbers here. Well, so we'll have 4th root and 4th root. I have 2 2's total so far, yes? How many do I need? 4, because if I have 4 2's, the 4th root of 2 to the 4th would simplify to 2, yes? If I have 2, how many more do I need? 2. So I need to multiply top and bottom by 2 squared. And no matter how many terms we have, if we have it in this kind of factored form, or the prime factorization form, 2 squared times all of these here, we're just looking to see what is the next number, next exponent that we need for it in the radical to simplify out completely. Here we have 2 squared. I need it to be 2 to the 4th. So I'm going to multiply by 2 squared. Now what that'll give us is, well, in the denominator, the 4th root of 2 to the 4th. The numerator is going to be the 4th root of 19 times 2 squared. Well, the denominator is now 2. Well, 19's prime. It has no other factors besides 1 and 19. So we don't have any way that multiplying it by 2 squared will give us a number we can take the 4th root of. So we'll just actually multiply those together. We'll do 4 times 19, which would be 6, carry the 3, 76. Now it'd be very tempting to say 76 divided by 2, but is the numerator actually 76? No, it's the 4th root of 76. So for us to be able to divide, we would actually either need a number in front of the root, front of the radical, or for that radical to actually simplify completely. If it simplified completely, we wouldn't have to mess with this at all. But that right there is your final answer. Questions on this here? No, but some of these here are helpful, especially on the ACT, because if it's asking for it in simplest form, simplest radical form, we know if there's a radical in the denominator, that's not the correct answer. We can throw that out immediately. Does that make sense? So some of this, especially on the ACT's math portion, if we can rationalize our way through it or think critically through it, we can eliminate a lot of the answer choices. Any questions on this here? No. We still have the other one, the cubed root of 500. We can try plugging that into the calculator and it give us a decimal. Now if we factor tree 500, well, we know 2 will go into it, and not 125. Well, that would be 2, 250. Well, 250 is 2 and 125. Well, 125 is 5 and 25, and 25 is 5 and. We do have 3 5s. And we have how many 2's? 2. Okay, that was interesting. So we can say the cubed root of 500 is 2 squared times 5 cubed. Can we take the cubed root of 2 squared? Well, no, we only have 2 of them, yes? So those will stay inside the cubed root, but our other number, 5, will come out completely, yes? So we will have a 5 out front. And the 2 squared would stay inside. And well, 2 squared is what? 4. So we can put it back together and not leave it as 2 squared, but just say 4. And that's it. Questions on any of this here? you ready for the next part? We want to write this in simplest form. We can't have a radical in the denominator. Well, to solve this here, we're going to use our rational conjugates. Which is really multiplying the numerator and denominator of this fraction by the denominator, but we changed the middle sign from plus to minus. Okay. And now we just need to multiply it through. So when we multiply by 1, well, it's just going to be 5 minus the square root of 3. When we did this with the denominator, our 5 times 5 is 25. 5 times negative square root of 3 is negative 5 square root of 3. Square root of 3 times 5 is 5 square root of 3. Minus, well, the square root of 3 squared. 5 minus square root of 3. Because since that's all that's on top, that's all we have to do. Now, hopefully that won't throw something up in the middle of the screen. Well, the negative 5 square root of 3 and 5 square root of 3 will actually cancel each other out, positive and negative. And we will have our 25. Yep. So we have 25 minus, well, the square root of 3 squared is just 3. (25 minus 3 is 22. Now, the graphing calculators don't do these because, again, it likes turning radicals of any kind into a decimal if it doesn't come out evenly. Now, there's a reason I picked this one here. Clear that out. 1 over 5 plus second square root of 3. 5 minus the square root of 3 over 22. The graphing, or the yellow calculators will actually simplify these for us. So there's not a whole lot of need for these here. So any of the rest of these here, even these here, even with radicals, this, the yellow calculators will still do it for us. If we had to do it by hand, we're multiplying top and bottom by the denominator, but flipping the signs. This is the assignment. You don't have to write it down right now. You can. And it's on page 252. I will also have it posted on Google Classroom for you to have it there. That's all we're doing here. Not too bad. Just a lot of manipulating the numbers.